So, yesterday we talked about ionic bonds. They cross the stairs. You think of salt. Ionic bonds, things that cross the stairs, have high melting points. They dissolve in water, and they conduct electricity. All right? Then we also talked about covalently bonded substances. They form molecules. They don't cross the stairs. You can include the H right here, okay? I'll put the H here because the H is not considered crossing the stairs, all right? Covalent bonds, everything comes from over here. They're called molecules. They have low melting points. Sometimes they don't even dissolve in water. They're not even solids at room temperature, most of them, right? And if they are solids at room temperature, they easily melt. They don't conduct electricity. So the ones that cross the stairs and the ones that come over here are opposites. Now this third type of bond are between metals. Here are the stairs. Metallic bonds are between metals, okay? And we're going to talk about them. We'll talk about metallic bonds real quick, okay? They are what hold metals together. All right, you want to write that down. They hold metals together. All right? Metallic bonds hold metals together. And we do not write formulas for them. Somebody else may be able to do this, but I'm not. We do not write formulas for metallic bonds. So we're going to be writing formulas for everything else. So if we look over here, and I'm not ironically pointing at these things with this metal bar. If copper and nickel are joined together, right? Or if we're making brass or bronze or something like that, then and you're joining multiple metals together, or even just what holds this copper pipe together, all right? Even just what holds this copper pipe together. Those are metallic bonds. So we can think about the properties of metallic bonds. If this thing's made out of metal, then that's a cool sound. Am I going to break this thing? No. What am I going to do to it? I'm going to dent it. That's right. Now the word for that is malleable. They are malleable. And a word for a hammer, another word for a hammer is a mallet. So this means hammerable. You can hammer them and shape them, okay? So metals that are metallically bonded are malleable. They're ductile. That means they can be spun into wires, right? Ductile means it can be spun into a wire, like copper wire, right? And they conduct electricity. They conduct electricity. We know that. The wires at your house are made out of copper, I hope. I hope you don't have aluminum wiring, because we've had some problems with aluminum wiring. So let's look at the one thing that I want to show you in this quick little video about metallic bonding. All right? We will talk about ionic bonding a little bit later and exactly how it works. But right now I'm going to show you the inner workings of metallic bonds. Let's say this is a section of metal. How about this is like a strip of aluminum foil? All right? Now in this aluminum foil, there are a lot of metal nuclei, okay? And I'm just going to make a little positive and put a circle around it, and we're going to call that the nucleus, okay? Obviously, there's not one proton in there. That would mean this was hydrogen, right? So if this is aluminum foil, all these little nuclei would have, what, 13 protons if it was aluminum, right? Isn't aluminum number 13 on the periodic table, right? So they have all these nuclei. And remember, we could draw a Bohr model for aluminum. It'd be 2, 8, and 3, right? 2, 8, 3. Everybody with me? Now these electrons, though, for aluminum, when aluminum's around a bunch of other aluminum atoms, the electron doesn't necessarily stay. The valence electrons don't necessarily stay with their own atom. You can wave a magnet near them, and the electrons will just skip over to the next atom. The electrons can move freely from one atom to the next. And that's crazy. Now, normally, if you have a metal, electrons are moving back and forth in random directions. But if you want to create a current of electricity, you can just take a big magnet and wave it past the metal, and all the electrons will move the same way. And that's something for physics. All right? So the electrons just go from atom to atom. They don't just stay with the one aluminum atom. And what we call this, we say that these atoms are swimming in, and you want to write this term down, an electron sea, or a sea of electrons. That's an important term. We say the atoms, or the nuclei of the atoms, are swimming in an electron sea, a sea of electrons. So the electrons on this aluminum atom, if it's around other aluminum atoms, they're pretty indifferent about which nuclei they go to. Does that make sense? And that doesn't happen with nonmetals. It just happens when metals are all around each other. Okay. So the electron sea, that's one reason we don't write formulas for this. All right? If there were some of these atoms were copper nuclei, the electrons would still be switching back and forth between the copper and the aluminum. So there's not like a specific formula or a specific ratio for us to write a formula with. Okay? Now, last thing I'm going to say, this electron sea is what gives this metal its unique ability to do this. Bam! All right, you hit it, right? You hit it, you just make a big dent in this. Well, no problem, because these atoms aren't rigidly held into place by their electrons, so they just shift over there, and then the electrons keep moving. Now, if we were talking about a more rigid structure, and if we're talking about a more rigid structure, like I don't know, this is probably a bad example, but let's say we had a cube of salt, right? Remember we talked about it being like a crystal lattice, correct? Well, these things are rigidly locked into place. So if you had a big cube of salt, like you've probably never seen one, but you could have salt in a big cube, and you smash this with a hammer, well, then it breaks apart and falls into smaller and smaller pieces, right? Because you're breaking the bonds that hold the NaCl's together. But that's not what's happening when you hit a piece of metal. It's malleable, and the electron sea is what gives it its properties, right? And again, metals conduct electricity. That's it. That's everything you need to know about metallic bonds.